Welcome to the deep dive. Imagine for a moment an AI that doesn't just write a neat little function, but tackles massive multi-file bugs across an entire software project.
Right.
Or even, adds complex new features to a sprawling code base. That's kind of the holy grail of automated software engineering, isn't it?
It really is.
Today, we're plunging into a groundbreaking paper that brings us remarkably closer to that reality, all thanks to something called code graph models, or CGMs.
Indeed. We've structured this deep dive for you to meticulously walk through the paper's innovative approach from the ground up, much like a scholarly breakdown following the paper itself.
Okay.
Our core mission today is really to demystify how open-source large language models, LLMs, can actually conquer these highly complex, what we call repository-level software engineering tasks. We're drawing our insights primarily from the core paper, Code Graph Model CGM, a graph-integrated large language model for repository-level software engineering tasks by Tao et al., along with their supporting project brief and study guide.
And why should this particular development matter to you, our listener? Because it directly confronts some of the biggest headaches in AI for coding right now. Things like the frustrating unpredictability of current solutions, the heavy reliance on incredibly expensive, often closed-source models, and, the very real data privacy concern.
Absolutely. Sending your code out.
Yeah, exactly. This paper charts a new agentless course for open-source LLMs that could fundamentally reshape how we approach software development. So let's start with the problem. We've seen LLMs make incredible strides with isolated coding tasks, seriously impressive, like over 90% accuracy on benchmarks such as human evil.
Yeah, they're great at those snippets.
But when it comes to real-world software engineering, that's a whole different ballgame. It's never just about one perfect function, is it?
That's spot on. When we talk about repository-level tasks, we're discussing challenges that demand a holistic understanding of an entire project. Think of fixing a tricky bug that might ripple across dozens of files and functions.
Right, a real tangled mess sometimes.
Yeah, exactly. Or implementing a new feature that touches multiple modules and requires deep integration. These aren't isolated puzzles. They require the AI to grasp the entire architecture.
So understanding how all the pieces interlock.
Precisely. The subtle interactions between them. It's like trying to fix a single faulty circuit in a sprawling city grid without understanding the entire power distribution system. You just can't.
And historically, the leading AI solutions for these kinds of complex, multi-file problems have leaned heavily on what are called LLM agents, often powered by the big proprietary models like GPT-4o or Claude 3.5 Sonnet.
That's been the main approach, yes.
What are the significant drawbacks there? Because on the surface, they sound pretty powerful.
Well, there are two critical drawbacks that emerge when you try to scale to these complex tasks. First, and perhaps most frustratingly, is their inherent unpredictability. These agent-driven mechanisms, they make sequential decisions, right? And if just one decision is slightly off, the errors can accumulate exponentially through the reasoning process.
So it snowballs.
It really does. Imagine an agent taking 30 or 40 turns, each building on the last, to solve a single issue. It becomes incredibly time-consuming, opaque to debug.
Hard to see where it went wrong.
Exactly. And incredibly difficult to pinpoint exactly where the agent went off the rails. You end up with this kind of black box that sometimes works and sometimes doesn't for reasons you can't easily trace.
Okay, that's unpredictability. What's the second major issue?
The second one is the reliance on these closed-source proprietary models. This creates enormous barriers. Accessibility is a major one. Not everyone can afford the high API costs.
Right. That locks a lot of people out.
It does. Then there's the inability to customize or fine-tune these models for your very specific internal needs or, your company's code styles. And critically, for many organizations, the security and privacy implications are just a non-starter. You're often sending sensitive proprietary code to an external API service.
Which introduces significant risk.
Yeah.
A huge risk. So this brings us to a truly ambitious question that the paper tackles head-on. Can open-source LLMs, without all those unpredictable agent-driven steps, actually be used to solve these repository-level tasks?
Yeah, it's a bold question.
Because at first glance, the odds seem stacked against them. Back in May 2025, closed-source agent systems could hit around, 55% resolution rate on benchmarks like SWE-bench Lite?
Roughly, yeah. Around 55%.
While the best open-source methods were way behind, maxing out around 30.67%. It looked like a massive gap.
It did look like a chasm, but the paper's resounding answer, validated by their results, is a clear and emphatic yes.
Okay. How?
Well, The secret sauce isn't just throwing more data at bigger open source models. It's fundamentally empowering them to truly understand entire code repositories.
Understand, not just process.
Exactly. This means grasping not just individual files or functions, but that incredibly intricate web of dependencies, interactions, and structural relationships that form the backbone of any large software project.
Okay, so having laid out the challenge, let's turn to the ingenious solution CGM proposes. How do code graph models actually achieve this full comprehension of a code base? What's the core idea?
The fundamental breakthrough of CGMs is their ability to jointly model both the semantic and the structural information within a code repository.
Semantic and structural. Okay, break that down.
Right. So semantic information is the meaning of the code, what each line, function, or class does. Structural information is how everything is connected, how functions call each other, how classes inherit, how files are organized.
Got it. Meaning versus connections.
Precisely. They achieve this by first constructing a code graph for each repository. This graph captures all those hierarchical and reference dependencies between the different code entities.
So once they have this rich connected code graph, how do they actually get an LLM to, well, integrate and understand this graph data? It's not just flat text anymore.
Exactly, and that's the clever part. They integrate this graph into the LLM through two primary mechanisms. First, there's semantic integration. This is where the actual textual content of the code nodes in the graph is carefully encoded and mapped directly into the LLM's input space. So the LLM essentially reads the code within each node.
Right, makes sense. What's the second part?
Second, and this is where it gets really innovative, is structural integration. Here, the graph structure, those connections, those lines between nodes, is directly woven into the LLM's attention mechanism.
Ah, into the attention itself.
Yes. This allows the LLM to understand not just what the code says in each chunk, but how different parts of the code relate to each other, forming a coherent whole. And all of this operates within a new, fixed-step, agentless graph retrieval augmented generation RAG framework. No unpredictable agent steps.
That's a fascinating two-pronged approach, semantic and structural integration within an agentless RA framework.
Yeah.
Let's really unpack this. How exactly is this code graph constructed? What's in it?
Okay, so to represent a repository, they build a directed graph, let's call it GVE. Think of V as the collection of nodes, the distinct code entities.
Like what kind of entities?
They range in granularity. You have the entire RPO itself as a top node, then down to package, individual files, generic text files, classes, functions, and even specific attributes within a class. Each of these nodes holds its original code content and its line range within the file. It's about breaking the repository down into meaningful interconnected chunks.
Okay, those are the nodes, V. What are the edges? E, the connections.
Right, E represents the edges, capturing the dependencies. There are two main types. First, hierarchical dependencies. You can picture these as solid lines in a diagram.
Like a contain relationship.
Exactly, like a file contains a function or a class contains an attribute. These are built by parsing the code's abstract syntax tree, or AST.
Okay, the AST gives the hierarchy. What's the second edge type?
The second type is reference dependencies. Think of these as dashed lines. These capture the dynamic interactions, like one function calling another function, or a class inheriting from another class, or one module importing another. These come from a lightweight semantic analysis. And interestingly, these reference dependencies can even introduce cycles, like recursive function calls, which is important for real-world code.
So you build this initial, very detailed graph with hierarchical and reference links. Is there any refinement after that? Seems like it could be a lot of overlapping text.
That's a perceptive question. Yes, there's a crucial post-processing step. After the initial graph construction, the text from child nodes is actually removed from their parent nodes.
Oh, interesting. Why?
It ensures that each node encapsulates a unique, non-redundant, and highly relevant code snippet. The result is what they call a text-rich graph, where every node provides distinct, valuable context without unnecessary duplication. It cleans things up nicely.
Fascinating. So you have this highly organized, text-rich code graph. Now, how do code graph models actually integrate that wealth of information into the LLM? This sounds like the core technical challenge.
Absolutely. This is where their semantic integration really shines. They don't just dump all the code text into the LLM linearly. Instead, the textual content of each graph node is transformed into special node tokens for the LLM.
Node tokens. Okay.
They use a pre-trained text encoder like Code T5 plus No to process this code text first. Now, for those long code snippets that exceed typical token limits, say 512 tokens.
Yeah, that happens all the time in real code.
Right. They cleverly break them into 512 token chunks. Each chunk is processed by the encoder, and then a small adapter, think of it as a compact two-layer MLP, a small neural network.
Okay, an adapter.
Yes. This adapter projects the encoder's output for that chunk into the LLM's input embedding space. And here's the really groundbreaking part.
Yeah.
Each of those 512 token chunks is compressed into a single node token.
Wait, 512 tokens become one token.
Exactly. This effectively extends the LLM's context length by a factor of 512 for the graph part.
Wow, that's enormous.
It is. It's like suddenly giving the LLM a vastly expanded working memory, allowing it to conceptually hold the context of an entire sprawling project in its mind, represented by these node tokens, rather than just a few isolated files worth of raw text.
That's a huge context boost, a real game changer for large code bases. Okay, that covers the semantic integration, getting the meaning in. What about the structural integration? How does the LLM understand the connections between these nodes?
That's handled by another brilliant innovation they call a graph-aware attention mask.
A special attention mask.
Yes. Normally, LLMs use a causal attention mask, meaning they only pay attention to previous tokens in a linear sequence. But here they replace that standard mask. This new mask is derived directly from the code graph's adjacency matrix, which is essentially a map showing which nodes are directly connected by those hierarchical or reference edges we talked about.
Okay, so the mask knows the graph structure.
Precisely. This mask forces the LLM's attention mechanism to only focus on neighboring nodes within the graph structure. It mimics the message passing concept from graph neural networks, but inside the transformer attention.
Interesting.
And crucially, this preserves the explicit structural relationships, the calls, the inheritances, the containments that would otherwise be completely lost if you just flattened the code into a long string of text.
Right, because related functions might end up really far apart in the flat text.
Exactly. This mask acts like a sophisticated internal map for the LLM. It tells it, hey, this function node here, it's directly connected to that class node over there. Pay attention to their relationship.
So the architecture beautifully maps the code graph to the LLM's understanding. But how do you train a model to actually internalize and leverage these complex structures effectively? It sounds like more than just standard LLM training.
You're absolutely right. The training is quite sophisticated. It involves two main phases. First, there's subgraph reconstruction pre-training. They call it graph to code.
Graph to code, okay.
Here, the model isn't just learning next token prediction. It learns to reconstruct the actual code content of nodes from randomly sampled subgraphs. This forces it to deeply understand the relationships and dependencies within those graph chunks.
So it learns the structure by trying to rebuild the code based on the graph connections.
Exactly. And they use a clever hierarchical approach during this. They place higher-level nodes like the REPO node at the beginning of the input sequence, then topologically sort the file nodes based on dependencies, and finally sort nodes within files by line number. This preserves the crucial logical structure.
Okay, that's the pre-training. What's the second phase?
The second phase is noisy fine-tuning. This is where the CGM is fine-tuned on actual real-world issue patch pairs, like those from the SWE-bench dataset. Give it the buggy code context as a graph and the issue description, and it learns to predict the patch.
Makes sense, but why noisy?
That's the smart part. They intentionally introduce noise into the prompts during this fine-tuning. For instance, they might include 10% irrelevant files in the context.
Files that have nothing to do with the bug.
Right, or they might even omit 10% of the Oracle files, meaning the files that actually need to be modified to fix the bug.
Why would they do that? Seems counterintuitive.
It makes the model incredibly robust. It learns to deal with imperfect information, to identify relevant code even when presented with distractions, and to potentially infer missing context. This helps it generalize much better to messy, real-world scenarios where the initial context you provide might not be perfectly curated or complete.
Okay, that makes sense. It toughens the model up for reality. This noisy fine-tuning, this leads perfectly into something you touched on earlier. How does all this, the graph architecture, the special training, connect to that agentless graph RAG framework you mentioned, the part that makes it operational?
Right, the graph RA framework. It's an ingenious four-module system specifically engineered to supercharge CGM's problem-solving abilities and streamline the entire process from user query to final patch.
And critically, it's agentless.
Exactly. That's key. It operates in fixed, predictable steps. Unlike those traditional agent-based systems that can have many interaction turns and sometimes spiral unpredictably, this is a defined pipeline.
What are the four modules?
They're the rewriter, the retriever, the re-ranker, and the reader. And the reader module is the CGM model itself. Importantly, it leverages powerful open-source models for its other components, like Qwen 2.572b Instruct for text processing and CGE Large for code embedding. It shows you don't necessarily need closed-source giants for every piece.
Okay, walk us through the flow. What does the rewriter do?
So the rewriter module takes your original user query, like fix the login timeout bug. It then enhances this query significantly to make it more useful for retrieval. It uses an extractor subcomponent to identify key code elements mentioned, like function names or classes, and an infer subcomponent to enrich the query semantics with more detailed descriptions, maybe inferring related concepts or likely file locations.
So it's like an intelligent preprocessor for my bug report. Makes it much more precise.
Exactly. It makes the initial vague request much more actionable for the system.
Yeah.
Then, the retriever module takes that enhanced query.
Okay, what's its job?
Its mission is to locate the most relevant anchor nodes within that vast code graph we discussed. Once it finds these starting points, it intelligently expands outwards to include all their one-hop neighbors, the directly connected pieces of code.
So the immediate neighborhood in the graph.
Right. And then it traces back to connect everything to the repository's root node. This creates a focused, connected subgraph of the repository that is most likely relevant to the problem, filtering out potentially millions of irrelevant lines of code.
Okay, that retrieval step narrows it down. But even a subgraph can be pretty large sometimes, right? How does it hone in on the exact code it needs to modify?
That's where the re-ranker module becomes absolute pivotal. It acts as a highly selective filter for the retrieved subgraph. Its job is to identify the top K, typically they use K5 files within that subgraph, that are most likely to need modification to resolve the issue.
Only 5 files. How does it pick them?
It does this in 2 smart stages. First, it narrows down the files based on surface-level relevance to the query and their file names. Then it goes deeper. It looks at the relevance of the file's skeleton, its structural outline, like the classes and functions it contains, to the enhanced query. This ensures the system focuses its main effort on the most promising areas for the fix.
That sounds really important for efficiency. And finally, the reader, the CGM model itself, gets all this curated information. What does it do?
The reader, our actual CGM, receives 2 crucial inputs based on the re-ranker's output. First, it gets the retrieved and re-ranked subgraph, presented as those special node tokens we discussed earlier. This gives it the global structural understanding of the relevant context.
The graph view.
Exactly. And alongside that, it receives the full textual content of just those selected top K files, presented as traditional text tokens. This provides the deep, precise local detail needed for modification.
So it gets both the big picture structure and the fine-grained detail of the most important files.
Precisely. This powerful combination of global structural context and focused local code content allows CGM to generate the final corrected code patch or the new feature implementation. It's the culmination of the whole pipeline where the trained model applies its understanding.
Okay, so we've walked through the problem, the innovative solution, the graph construction, the integration, the training, and this clever array framework. Now for the crucial part, the results. What does this all mean for real-world performance? How did CGM actually stack up? The results for repository-level issue fixing are genuinely impressive, particularly for an open-source approach. CGM was rigorously evaluated on standard benchmarks like SWE-bench Lite and SWE-bench verified for Python, and also SWE-bench Java verified for Java.
And the key metric is resolution rate.
Yes, the percentage of issues the system successfully resolved by generating a correct patch. The numbers for CGM's SWE-PyAY, which is their Python-optimized model, are quite remarkable. They achieved a 43.00% resolution rate on SWE-bench Lite.
43%. How does that compare? You mentioned earlier the previous open source best was around 30%.
Exactly. That 43% places it first among open source models, second among open source systems overall, some systems combine multiple models or tools, and 8th overall among all systems evaluated at the time, including those using powerful closed-source models like GPT-4o and Cloud 3.5 Sonnet.
Wow, 8th overall, even beating some closed-source setups.
Yes, that's the striking part. It dramatically outperformed the previous best open-source model-based method, Moteless plus DeepSeek v3, by over 12 percentage points. And what's truly astonishing, as you noted, is that it even slightly surpassed agentless plus Claude 3.5 Sonnet and significantly outperformed agentless plus GPT-4o in some configurations,
despite using a simpler RAG framework and being built entirely on open source components.
That really does narrow the gap. It suggests the architecture itself is incredibly powerful.
It strongly suggests that yes, it shows that explicitly modeling the code structure can be more effective than just relying on massive scale or complex agent interactions for these tasks. And on the larger, more challenging SWE-bench verified dataset, CGM SWE-PI also took the top spot among open weight models with a 50.4 year-event resolution rate. And for Java, their CGM multimodel achieved 14.29% on SWE-bench Java verified, clearly outclassing systems like SW Agent in that domain.
Those are really compelling numbers for fixing bugs. What about repository-level code completion? That's a different, maybe broader task.
Right, completing code across multiple files based on context. They evaluated that on benchmarks like cross-code eval and complex code eval using metrics like edit match, EM, and edit similarity, ES.
And how did CGM do there?
CGM Multi performed on par with, or sometimes exceeded, other very large open-source language models like Mistral 123B and DeepSeek 236B on cross-code eval, which tests cross-file understanding. But where it really shone was on complex code eval, which specifically targets more complex, context-heavy completion scenarios. It greatly outperformed the baselines there, achieving 47.000% EM on Java and 43.00% EM on Python.
So it excels when the complexity increases.
That's what the results suggest. Its ability to leverage the comprehensive subgraph analysis seems to give it a distinct advantage when the completion task requires understanding intricate dependencies across a repository. It also typically outperformed other RAG methods like standard BM25 keyword retrieval and another method called RLCoder.
Okay. And you mentioned RepoFuse earlier, which also uses code graphs.
Yes, and CGM's superiority over RepoFuse is particularly telling. RepoFuse also uses code graphs, but it tends to flatten the graph information into linear text sequences before feeding it to the LLM.
Ah, losing the explicit structure again.
Exactly. CGM, by contrast, explicitly integrates that structural information using the node tokens and the graph-aware attention mask. The comparisons strongly suggest that how you integrate the graph matters immensely, and CGM's approach of preserving explicit dependencies is more effective.
This is where it gets really interesting for understanding why it works. They didn't just show great results, they performed ablation studies, right? Pulling the system apart piece by piece.
They did, and these studies are crucial for validating the design choices. They systematically removed or modified components to see the impact on performance.
What were the key takeaways? What broke when they removed it?
Well, they confirmed that pretty much every component is crucial, the entire GraphRE framework, for example. And within that, the re-ranker module, the one that selects the top K files, proved absolutely pivotal.
How big was the impact of removing the re-ranker?
Massive. Removing just a re-ranker caused a huge 24.67% drop in resolution rate on SWE-bench Lite.
Wow, nearly 25%, just from not filtering the files properly?
It highlights that even with sophisticated graph understanding in the reader, CGM, knowing where to focus, that understanding is critical. You can't just feed the whole subgraph effectively. You need that intelligent filtering.
Like the librarian analogy you used earlier.
Exactly. And removing the entire RAG module, forcing the CGM model to work with just the raw issue description and maybe some basic retrieval, led to an even larger 33.33% performance decrease. It underlines the necessity of that whole retrieval and refinement pipeline.
Okay, so the RA framework is essential. What about the core CGM architecture itself, the semantic and structural integration?
Also essential. For instance, removing that custom graph-aware attention mask.
Yeah.
The key to structural integration led to a significant 8.61% drop in edit match for Java code completion.
So the model really needs that structural guidance from the mask.
It absolutely does. It shows that simply encoding the code text into node tokens, semantic integration, isn't enough on its own. The LLM truly needs to see those connections provided by the mask.
And the special pre-training, the graph-to-code part.
That also made a noticeable difference. The subgraph reconstruction pre-training contributed significantly, showing a 7.65% improvement in edit match compared to just starting with a standard pre-trained model and doing the noisy fine-tuning. It demonstrates that teaching the model to explicitly understand graph structure during pre-training pays off.
So these ablation studies really paint a clear picture. It's not just one magic bullet, but the synergistic combination of the graph representation, the specific integration mechanisms, the tailored training, and the smart RAG framework that delivers these results.
Precisely. Each piece plays a vital role, and their unique design choices seem truly effective.
So we've covered the impressive capabilities and the validation. But like any cutting-edge tech, it must have boundaries. What are the current limitations of CGM mentioned in the paper?
The primary limitation highlighted is the language focus. The current work is validated mainly on Python and Java.
Both object-oriented languages.
Exactly. Both are object-oriented, which influences how you might naturally structure a code graph. Classes, methods, inheritance. This raises important questions about extending CGM to other programming paradigms.
Like what?
Well, think about multi-paradigm languages like Rust, which mixes imperative, object-oriented, and functional features. Or purely functional languages like Haskell, with very different structural concepts like type classes and function composition.
So building the graph itself might need rethinking.
Potentially, yes. It would require a careful re-examination of how to best construct the code graph, what nodes, what edges, to accurately capture and represent those paradigm-specific structures and dependencies effectively. It's not necessarily a trivial extension, but it's a really exciting and necessary direction for future work to make this approach more universal.
What a deep dive today. CGM truly represents a significant advancement, it feels like. It emphatically demonstrates that open source LLMs can achieve competitive, sometimes even superior performance in these incredibly complex repository-level software engineering tasks.
It really does push the boundaries for open source.
And crucially, it does this without relying on those sometimes unpredictable agent-based approaches or the often restrictive, expensive closed-source models. The core brilliance seems to be its seamless integration of both the codes, meaning the semantic part, and its structure, through that specialized encoder-adapter framework and those clever graph-aware attention mechanisms.
That combination is key.
And when you combine that core model with its custom graph RAG framework for efficient retrieval and focus, it really sets a new benchmark for what open source models can achieve in real-world issue-fixing scenarios. It establishes a clear, powerful new direction for building transparent, accessible, and highly effective tools for automated software engineering.
It truly does shift the landscape, I think. It shows a concrete path forward. So for you, our listener, here's maybe a thought to mull over as we wrap up. Given CGM's incredible success in bridging that performance gap for open source models, what new possibilities does this unlock? Think about smaller development teams or maybe individual open source contributors who might not have the budget for expensive proprietary AI tools. What could they build with this kind of capability? And maybe how might this accelerate innovation and collaboration within the vibrant open source software community itself, now that such powerful tools are potentially within reach?
That's a great question to ponder. We definitely encourage you to explore more about this exciting development if it piqued your interest. Until next time on The Deep Dive, keep digging deeper.